So let me start by showing you a kind of like a high-level outline of what I'm planning to talk about. So I'll talk about analyzing personal data with the goal of kind of protecting the privacy of the data. And protecting privacy seems to be one of these things where it's pretty hard to even define what it means to protect privacy, let alone to do it. So it's pretty hard to start right away from things that do work. So instead, I'm going to start from some things that do not work and why they don't seem to work, and in what sort of sense, in what situations they don't seem to work. Okay, so I'll start with some attacks against kind of let's say naive or not so naive sometimes methods to protect privacy of people. Then I'll introduce differential privacy. And sorry, was there a question? Okay, then I'll introduce differential privacy. So I'll kind of give semi-mathematical definition. I'll talk about some like basic techniques to achieve differential privacy. And then towards the end, I'll talk a bit more about kind of a few more advanced techniques that allow you to do better in some cases. And at the end, we can have some time for discussion. And I'm looking forward to that. So again, stop me anytime. Okay. So let me start with, like I said, let me start with attacks, okay, with things that basically do not work. Let me really first start with kind of the basic, very high-level problem that I'm considering. So we'll talk about analyzing personal information or information about people. This slide used to say sensitive information, and after some discussions, I've decided to not really get into what is sensitive, what is not, but let's say we have some data. The data is about people, and for one reason or another, whether it's kind of contractual obligations, legal obligations, or set of some moral considerations, we consider the data private, and we would like to preserve the privacy of the people represented in the data. Okay, so this is the problem. And the question is how to analyze data like this. Okay, what do we do about this? This is the basic problem that will be sort of throughout the talk. Okay, and approach number one will be, okay, you can like, one thing that I think should always be on the table is you do not collect information like this, so you do not analyze it. You sort of maybe collect it, but you keep it under a lock, you secure it as well as you can, and you don't analyze it, or you don't like open it up to the world ever. And this is fairly good in terms of protecting privacy. And it should be something that's on the table. Maybe sometimes you should not collect certain types of data, and that's like a worthwhile conversation to have. But so that I don't stop the talk here, right? Let's say that we're not in a situation where this is something we want to do. You know, you cannot stop collecting census, or you cannot and you should not stop collecting census data. You should not stop doing scientific studies when they can have some like real positive impact on society. There are many situations where just the benefits of this data, when it's analyzed properly, can be large enough that you do want to analyze it, that you do want to actually grapple with this problem of how do you analyze this data. It's so useful. You can have, like, we can learn something from it, how to analyze it without hurting the privacy of the people that this data is about. Okay, so let's say we're not taking approach one. Approach two, on a high level, is something that's still done a lot, and something you still hear about. Something that's to some extent still kind of written in regulations also. And this is the following. So what I call approach two is removing what we call personally identifying information. So the idea here is that there are certain pieces of information that identify a person, let's say uniquely. A bit hard to define what that means, which is part of the problem, but there's certain pieces of information that clearly identify a person. You know, my name more or less identifies me, at least in Canada. If you go to Bulgaria, there are like, I don't know how many thousand Aleksandar Nikolovs, but in Canada, I'm sort of unique by my name already, probably. My social insurance number identifies me, my address identifies me up to like a set of two. You know, just like some things that are very clearly identified. And the idea of sort of some, let's say, more naive approaches to protecting privacy is to take the data and scrub it clean from personally identifying information. And then we consider that data safe and it can be analyzed. Okay, so of course, it really depends how we implement this. But basically, this seems to be an approach that is very hard to get right and often fails. And there's some very well-known failures of this approach, this like naive approach to protecting privacy. I've mentioned some famous examples here. There's a Netflix challenge, which led to a class action lawsuit. There's the AO search logs. There's a famous example with identifying the health records of the former governor of Massachusetts. So from a while ago, I'm not going to go into these very well-known examples because I'm a little tired of them, but I'll explain an example that's more recent, just from like a bit more than a year ago, which is from Australia, from a paper of Cullinane, Rubinstein, and Teague. And let me just see, I think there's a chat message.
Yeah, question from Christina.
Christina asks.
Sorry, I didn't mean to interrupt. I just wanted to make sure I didn't forget also in case I got called out. But there's another concern that sort of is related to those two, and maybe you can speak to this, but with the census data, we have to protect, we can't even reveal whether or not a firm is in the firm data, much less any details about it. And there seems to be a distinction between being in the data, but completely obscured versus knowledge of being in the data. And I didn't know to what extent these two concerns can be disentangled and under what circumstances.
It's a good question. I think that's part of the problem around these discussions is exactly how can we disentangle these things. And yeah, I think something that maybe can be frustrating about the approach I'm going to eventually talk about, the differential privacy approach, is that it avoids trying to disentangle these things and basically says that you should not even be able to tell if someone is in the data set. And the thinking there is that even in a very worst case setting, this seems pretty safe. It's possible that you can tell someone is in the data set, but you still cannot really break their privacy in a meaningful way. But I think we just don't have very good ways to define what that means that are sort of robust. But yeah, we should probably talk more about this.
It sounds like maybe addressing the whether you're in the data set is at least a sufficient condition for these other concerns.
Yeah, I would say, or like not being able to tell if you're in the data set is maybe a sufficient condition for protecting privacy, but maybe it's not necessary, if that makes sense. Okay.
Thank you.
And this will come back. Thank you. Nice question. Okay. Thanks. Yeah. Welcome questions. Let me get back to this example. Let me try to give you one example of how just like removing personally identifying information in a naive way can fail. Okay, this is an attack from Australia by these three researchers, Cullinane, Rubinstein, and Teague. This is just from 2019. Let me sort of describe the attack. Apologies to those who have read the blog post that we had with Nikolov. This is sort of there as well. So this talk has some overlap with that. I hope I don't bore you here, but there will be stuff here that's not in the doc. Sorry, not in the blog post. Okay, so what is the setting here? What happened? The state government in the state of Victoria in Australia released a data set, which was a data set about a travel card. So what I mean by travel card is something like our Presto card. So the card is called Mikey. It's a travel card that can be used in the state of Victoria, and it allows you to get on and off different kinds of public transit. So you tap it on when you're getting on the bus or light rail or a commuter rail or subway, and you tap it off when you get off. And then you get charged, depending on how much you've traveled. So just to kind of make this closer to home, let's imagine this is Presto, not Mikey, but this is an attack against something in Australia, not against Presto, just to maybe also like not worry you too much. Okay, so the government in Australia wanted to, or like they organized a hackathon where they took a data set that contained information about how people use this Mikey card, this travel card. And they thought at least they de-identified this data set or they anonymized this data set. And they definitely did some of the basic things, like they definitely removed names of people, addresses of people who registered their cards. They also did not publish the actual serial numbers of the cards. They seem to have hashed them in some random way so that you get an identifier for each card, but you don't get the actual serial number of the card. So if you just take a card and you look at the serial number, you won't be able to then go and like look it up in the data set. So that much they did. And then after that, what the data set contains is a bunch of kind of data points or like rows, where each data point tells you when and where a particular card was used. Like for any tap on and tap off event, you have this like random hash identifier for the card and when and where that card was used. And the idea was that this data can be made available. It's like de-identified, should be safe. It can now be made available to people participating in this hackathon who can then sort of do their best analysis of it and come up with maybe ways to improve Victoria's public transit system. Let me see, one more question, maybe. Not quite, thank you. Thank you for the link. Good. All right, so let me say, why is this data set not really de-identified, or like not de-identified in a way that's useful, that's like really, that really does anything, that really protects the privacy of the people in the data? Or like, let me really tell you what the researchers did is actually what I'm saying. So, okay, so there's like a two-step attack, basically. Step one, it looks very innocuous. You can go and find your own card, okay? So these cards, just like Presto cards, are registered. So you can register the card on a website, and then that website tells you exactly when and where you use the card. So you can go and look up your own travel history. So for this is something I created in the before times. This like slide is taken from an older talk. So in the before times, I sometimes would take the Union Pearson Express and go to the airport and go somewhere. If you like remember these times. So this is from my own actual travel history. Sometime in August, I went somewhere, I guess. Okay, and you see, I know exactly when and where I use my card. And now, just looking up a few trips that you've taken, you can look up these trips in the data set, and you can see which cards in the data set match those trips exactly. So which other cards were used at the exact same times and places as your card was used. And it turns out that almost everyone's card can be identified uniquely from 2 or 3 trips. Like this is kind of a running theme with these kind of attacks. It's almost always the case that a surprisingly small number of pieces of information that look innocuous in isolation, you combine them and you can identify a person uniquely. And this is the case here too. So just like 2 or 3 trips on average tend to identify a card uniquely. And now you can find your card in the data set. And you know sort of which random hash in the data set corresponds to your own card. Okay, so you've kind of de-anonymized or de-identified your own personal information, which feels fine. It's not a huge privacy leak if you basically learn something that you already know in a way. But the new piece of information you're learning is which card in the data set is yours. Okay, this is the crucial thing. And this you can leverage to learn more about other people. Okay. So this is the second step, where you can, for example, find out information about someone you work with. Okay, so here's how you can identify the card of a coworker. I think it's like a nice programming exercise for a student, maybe. So I'm not even sure you need so much programming, to be honest. Anyways, so what you do, let's say you want to find out what a coworker does on weekends. And let's say you know that maybe on these particular days, you took the light rail or the streetcar back home with this particular coworker. You can look up exactly when you took the streetcar home. And then you know that your coworker was with you. So you know that they used their card at the same time. Maybe you also did had one work dinner with them. So you know that time you went somewhere together. So you can look up those few trips that you took with your coworker, and you can kind of cross-reference which are the cards that were used together with your card for those few trips. And again, usually there's a unique match. There's a unique card that was used with your card, with your card at these times and places. It allows you to uniquely identify the card of your coworker. And now that you know the card of your coworker, which card in the data set is your coworker's card, you can find out where they've been on weekends, for example, which feels problematic, right? If you can find out where your coworker goes at any time. And by the way, this data set was quite extensive. It contained a lot of trips. Maybe not every trip that was ever, taken, but it was pretty extensive. Okay, so this is one thing you could do. A different attack against someone maybe that you don't know as closely as your coworker, and this was kind of cute that they could do this kind of attack. Turns out there's a member of parliament in Victoria in Australia who likes to tweet about their about times that they took the public transit. So this person, Anthony Carbine, or Carbines, I'm not sure, sorry, he's a proud member of parliament who's proud of the local public transit system and how well it works. So he often proudly tweets about when and where he took a bus and everything worked great. This is an actual tweet that I also did a screen cap of. So then you can take his tweets, it's a surprising number of them, and you can again correlate them with the data set and find out which card is his and where he goes when he's not tweeting about it. And again, feels kind of problematic. Okay, so this is, I think, an interesting attack. You can see it's very easy to carry out, by the way. It doesn't require anything very sophisticated. Let me try to draw some lessons. Right. You just see the chat. So Ron says it would be easy to spy on someone. Yeah, that is true. It would be easy to get this sort of information that you need for this kind of attack. I agree. Okay, maybe this is another lesson, but let me try to draw some lessons that lead me kind of to what I want to talk about in my talk later. And then, which I think are important lessons. So one thing that we learn from these sorts of attacks is that essentially everything can be person identifiable, or it's at least very hard to say what is not person identifiable. We often get surprised how seemingly innocuous information, a few innocuous pieces of information combined together, can uniquely identify a person. And over again, with every next attack, we find a new way that this happens. Okay, so surprisingly, a few pieces of information actually make us unique. In a way, what we do is somehow very high dimensional, and we're, I guess, surprisingly unique. Maybe there's some philosophical point there. I'm not sure, but in any case, very hard to say what is personally identifiable, or rather, very hard to say what is not personally identifiable. Turns out that almost everything could be. Another, I think, important lesson here is that the person who's attacking you is already invested in attacking your privacy. If they're already invested, they probably already know a lot about you, and they can leverage what they know to make it easier to attack, or to make it easier to carry out the attack. And you don't really know what exactly they may know. I guess related to that, it's hard to say what is person identifiable, because what also matters is who is doing the identifying and what they already know about you. And the answer to this question may be different for different people, and we're trying to usually protect the privacy of many people, not just a single person. And it's really hard to make justifiable assumptions about who the attackers are and what they already know, which makes it hard to kind of say what is person identifiable and what is not. And something that makes this even harder is that people become even more easily person identifiable when you start linking different sources of data. And this is you can see this Twitter example and correlating Twitter with the data set that was released as one example of this. You can kind of link Twitter information, various kinds of publicly available information about people, with a data set, and this linking can end up disclosing more than just each source of information in isolation. And you can expect even more information will be released about you in the future, which kind of makes things trickier. Okay, so this complicates matters as well. Okay, so this is what I will say, at least for now, about PII. I mean, about person identifying information. There's some attempts to kind of address that by defining what called quasi-identifiers, but I think they basically suffer the same problems or similar problems. Okay, so now I'll shift gears a little bit and try and talk a little bit about something that's actually a bit closer to what I'll eventually talk about, which is differential privacy, which is the following slightly different approach. So maybe one reaction to this Mikey or potential Presto example is that maybe what's problematic with it is that the data is too fine-grained. Every data point is a data point about a single trip, even not even about a single person. And maybe one way to make things safer is to aggregate, to kind of only publish some aggregate statistics about trips taken on Mondays or something like that, rather than publish granular data about every single trip. And this is starting to sound reasonable to me, this sort of idea that aggregate data is inherently somehow safer than fine-grained data. I mean, on a high level, this sounds reasonable, but it again turns out to be subtle how to do this right. And the problem are the following kind of simple observation. Like I think, okay, it's not the problem, but I think the problem is illustrated by the following kind of simple observation. You can take two aggregate pieces of information or more aggregate pieces of information, two or more, and link them together to learn something about a specific person, something that's not aggregate anymore. So just give a simple example, and then I'll talk about a bit more sophisticated examples. Let's say I ask how many computer science professors in the University of Toronto like to sing in the shower. And let's say I ask how many computer science professors in the University of Toronto who are not born in Bulgaria like to sing in the shower. And I get these two numbers. I subtract the second number from the first number. And now this difference just tells me, do I like to sing in the shower or not? Because I'm the only Bulgarian-born computer science professor in the University of Toronto, as far as I know, for now. Okay, so, so both of these pieces of information seem aggregate, but the combination of them says something about me. Okay, so this seems kind of maybe too simple, and maybe there's some easy ways to get around this kind of problem. But it turns out that this kind of idea of combining aggregate information to learn personal information can actually be made quite powerful, and it's quite hard to avoid that. Okay, so the next thing I want to talk about is what are called reconstruction attacks. This goes back to work of Dino and Nissim, 2003. Who showed that, on a high level, you can take kind of answers to many aggregate questions about a data set, and even these answers could be noisy, and you can still learn personal data from these answers. So let me describe this in a little bit more detail. The attack is pretty flexible, but here's one setting of the attack. Let's say that you can kind of disclose to the public some data set that looks like this table. So each row corresponds to a person. Each column corresponds to some feature of the data. So here I have sex and education, and you can imagine there are other features. And these features we kind of consider to be safe, and they're known to everybody. Let's say we've removed names and stuff like that from here. And then there's a hidden column, which in this case is the very private information of whether this person likes to sing in the shower. And this is not published. Instead, what we are allowed to publish are answers to counting questions about this private information here. Okay, so we are allowed to answer questions of the type: how many people in the data set who satisfy some property sing in the shower? For example, what is the fraction of shower singing PhD students? What is the fraction? Whoops, sorry. What is the fraction of shower singing male PhD, or maybe not students, people with a PhD, male people with a PhD who sing in the shower, and so on. And let's say you get an approximate noisy answer to a lot of questions of this type. And here the noise there's no assumption of what the noise is. The noise can come from anywhere. So the noise could be, as is kind of commonly done in, is used to be done in the census, for example, the noise could be like you kind of do some thresholding, you round things up, or you could just inject random noise also. There's no assumption of what the noise is, but you can kind of, like it's kind of reasonable to think that because these are aggregate questions and you're only giving noisy answers to them, this should be fairly private. But counterintuitively, I think, Dino and Nissim showed that, under some assumptions, you can usually reconstruct from these noisy answers to these simple counting questions. You can usually, even with quite a bit of noise, you can still usually reconstruct the sensitive column here almost exactly. So you can, for every person, you can almost exactly find out, are they shower singer or not? And what I mean by almost exactly is I mean that you have the right guess for most people. Okay. Which kind of tells you that this aggregate is private kind of thinking is also, I think it's on the right track, but it's also hard to get right. You have to be careful. Let me sort of give a little bit more detail about, let me give a little bit more detail about how this kind of attack works, just to give you a little bit of intuition. So the attack is in fact quite simple. I mean, the details of how to make it computationally efficient can be less simple, but the attack itself, the idea is very simple. You have all these answers to these like noisy counting questions that tell you, let's say that approximately 3 people in the data set have a PhD and like to sing in the shower, and approximately 0 up to some margin of error of them are male and so on. Let's say you have a bunch of these noisy answers. What you do is you just try to find any setting of the values in this column, any setting that's consistent with these noisy answers up to the margin of error. Okay, so basically you try to find what you as an attacker, now you don't know these values, you just try to find any values that are consistent with what you've been told. Again, let's say you have some idea of what the margin of error is. Or if you don't know what the margin of error is, you just try to find the answers, you just try to find the values for this shower singing attribute that give you answers to your queries that are as close as possible to the answers that you actually were given. And you can usually, maybe with a little bit of cleverness, you can write this as some sort of constraint satisfaction problem or a linear program. You can usually write this in a way that makes it a problem that can be efficiently solved on a computer. Maybe with a bunch of work, I mean, with a, by efficiently solvable, I don't mean that you don't need, large computational power. Sometimes these things are like fairly large computations, but they can be done. Okay, so that's the idea. That's basically how the attack works. And the idea is that if the queries you're asking are sufficiently uncorrelated, so every new query kind of really tells you like a new piece of information, this kind of simple approach works. And the basic idea is that the values you found, because they're consistent with the answers you were given, they must also be close to the true values of this hidden attribute. Because you can do some computations, you can convince yourself that if you chose many wrong values in this column, then this column would have not been consistent with the answers you were given. Okay, so if you have many wrong hidden values here, this would lead to like very different answers to the queries than the ones you were given, and then you can rule out settings of the hidden attribute that have many wrong values because of that. Okay, and so this is not quite precise. What does it mean that the queries are sufficiently uncorrelated? But you can give actually precise mathematical conditions that guarantee that you can carry out these kind of reconstruction attacks. Okay, and one place we did that is in a paper that's pretty old now with my advisor Muthu Krishnan in 2012. We kind of quantified what you need from these queries and what you need from how big the noise is in order for this attack to work. Okay, let me tell you that these attacks are not just theoretical, so that they have been carried out, and the attacks are pretty robust, and it's with some cleverness you can often adapt the attacks even to settings that don't look exactly like the setting I'm describing here. One example is pretty recent, is work by Cohen and Nissim from 2020, where they show that like a commercial kind of query answering system that's designed to preserve privacy, it's called Diffix, is actually vulnerable to this kind of attack. So this was a system that was meant to protect privacy, but not kind of add as much noise as differential privacy would tell you that you need to add. They were basically trying to protect privacy with too little noise. And maybe not so surprisingly, it turned out that you can then carry out this attack against the system, and you can actually break its privacy, so it doesn't really provide strong privacy protection. And this is one example. And another interesting example is some work by the US Census Bureau, which I should know better, but my understanding is that they took the 2010 census, decennial census that was published, and they discovered that from that census, they can reconstruct kind of the raw data for 45% of the population. And if they allow reconstructing, I think, year of birth up to an error of ±1, so if they allow like an error of 1 year in terms of when you were born, then under that like weaker form of reconstruction, you can reconstruct the raw data of 71% of the population, which is what I think incentivized the US Census to move to techniques with kind of formal privacy protection like differential privacy. Good. Okay, so and let me now, for the last part of my talk, let me now just describe what is differential privacy. What is this framework that has kind of formal privacy protection guarantees, which avoids, I would say, like most of these pitfalls that I talked about so far, although potentially comes with kind of new issues which are interesting to think about. Okay, but this is like one tool we have to avoid these, to kind of protect against these kinds of attacks that I've talked about so far. Okay, so here I'm repeating again something that you probably saw in a talk by Nikolov a couple of weeks ago, but I think it's fair to remind everyone and maybe have a slightly different perspective on what how you define differential privacy, although I think it's mostly the same. Okay, so let me now say, what is differential privacy? Again, this is one way we have, or maybe the only way we have really of defining what it means to protect privacy, which has some strong guarantees. Okay, so this is something proposed by Dwork, McSherry, Nissim, and Smith from 2006. It's a definition that's based sort of on a thought experiment. But maybe before I describe the thought experiment, one thing I should say first is that the way we think about this is the following. It's a little bit different from what you saw in the beginning of my talk, where, for example, with the Mikey example, where we had some data set and what was done to the data set was like to try to make it safe by kind of removing something from it. This is not the framework in which differential privacy works, which is kind of partly the point. In differential privacy, instead, we think about the following. We have some private data set, which is going to be given to some algorithm, and the algorithm is going to spit out something useful that it computes from that data. So the algorithm can compute some answers to these kind of counting queries that we talked about so far, or it can or the algorithm could use the data to train a deep learning model on the data. It can use the data to fit some regression, do some hypothesis testing, do some statistics on the data. So whatever it is, the algorithm takes the data and outputs something. And what we define to be private or privacy preserving is the algorithm. Okay, so what we're going to now be talking about is how the algorithm deals with the data. And depending on how the algorithm deals with the data, the algorithm may, protect the privacy of the data or not. Okay, so what's important here is that what's private is the algorithm now, not the data itself. But we're going to focus on what makes an algorithm privacy preserving. Okay, and the way we define that is by thinking about a thought experiment. Okay, so the thought experiment is the following. In like one possible world, we give a data set, call it X, to the algorithm, and the algorithm spits something out. Like the algorithm produces some output. And then we have an alternative world in which we take that same data set, but we take the data of one person. Maybe this row in the data set corresponds to me. I take this data set and I change it. I change this row in the data. I change my data in the data set in some arbitrary way. Okay, so I take the data of one person and I change it in some arbitrary way, and I produce a new data set X prime. And in my thought experiment, I give this second alternative data set to the same algorithm, and the algorithm again spits something out. And what we want to guarantee is that in these two possible universes, the algorithm produces almost the same thing, in the sense that the algorithm should behave in almost the same way. Okay. What does this really mean? Really, these algorithms are random. So they, inside the computer, the algorithm flips some random coins and makes some random decisions. And then it produces some random output based on the data set. And the random output that the algorithm A produces on data set X, and the random output that the algorithm A produces on data set X prime, those two random outputs should have almost the same probability distribution. Okay. And this is what I've tried to show as this graph. Okay, but in some sense, on a high level, what you want to say is that the algorithm behaves almost the same way for those two alternative data sets. The one data set, think of one data set as having my data in it, and the other data set having some fake data in it, in place of my data. But everyone else's data point remains the same. Okay, so this is differential privacy on a high level. Let me get a bit more specific about what differential privacy is. So we said that the algorithm is differentially private if for any two such alternative data sets, X and X prime, where they differ in only the data of one person, and all possible outputs that the algorithm can produce, I should have that the algorithm producing output O on input data set X, okay, this should be about as likely as the algorithm producing the same output, but on data set X prime. Okay, so any possible output of the algorithm should be approximately equally likely, no matter if I change the data of one person or not. Okay, it's like a slightly more mathematical definition, which those who've seen differential privacy before will see is a bit different from the usual definition. It's like morally the same. Basically, you want the ratio of these two likelihoods, these two probabilities, in these two alternative worlds to be close to 1. Okay, so almost the same likelihood in these two cases. What this means, intuitively, what this definition means is that whatever an adversary learns about me from the output of the algorithm, they could have learned the same even without my data. Okay, because I could have changed my data to something else, and I know that the algorithm would have behaved in almost the same way. So intuitively, the adversary would have learned almost the same if my data was completely different or even removed from the data set. Okay, so really what an adversary is learning from the output of the algorithm is not really about me, because they could have learned that even without my data there. And I think one important thing that this definition achieves is that it gives us a way to separate statistical information from personal information. So what I mean by statistical information is something like smoking causes cancer, something that's a fact of the universe, like a fact of nature, some like statistical correlation that's not about any single person. So if I take some big data set about like smoking and incidences of different cancers, if I change the data of any single person, that's not really going to significantly change the correlation between smoking and different cancers, okay? The statistical correlation is not about one person. And this is the kind of thing that a differential private algorithm will be able to discover from the data, because this is the kind of thing that's not about a single person. What a differential private algorithm cannot discover from the data is information that is really tied to a single person, okay? So, for example, the algorithm shouldn't be able to find out from the data if I smoke, because whether I smoke changes significantly. Like, the algorithm has no way to know that I smoke, intuitively at least, if the data set is changed so that my data point that may say that I smoke or that I don't is changed. Okay, so I think this is one achievement of this. Yes.
Yeah, can I ask a question? Just sorry to interrupt you, because so you introduced us to like the reconstruction with the Mikey data set or the Presto, and we're talking. I just want to make sure I'm clear that so differential privacy would help if so the Presto, the Mikey, is it Mikey problem?
Yeah, I think so.
It's the first time I've heard of that one. So that's the problem of putting the data set in a publicly available place.
Yeah.
Now, this is about releasing results from a model or the application of an algorithm.
Yeah.
I just want to make sure I'm clear about that, because the setup in terms of that risk to privacy is quite different from what differential privacy that you're describing here can address, correct?
Yes, that is correct. I hope that was not too confusing. Yeah, so generally, it seems pretty hard to do the kind of thing that they did with the Mikey dataset, where they release the dataset and to do that in a safe way. There's some ways to do that with differential privacy also, where you really come up with a fake dataset with the same statistical properties. Basically, think of GANs or something like that if you want. But besides that, part of the reason why I talked about this Mikey dataset is to kind of drive the point that it seems hard to release data, even if you modify it a little bit and do that in a safe way. Whereas if we instead aim to release some model about the data or the result of some statistical computation about the data, we have some tools to do that and provide strong protection.
Right, great, thank you.
Thanks, good question. Okay, good. Okay, so this is what I'll say about the definition. Again, good. So again, I think one of the achievements of this definition is to kind of allow us to separate what is statistical information versus what is personal information about a person. And with that, the definition also tells us what it means to protect personal information about a person. Okay. Good. Again, please, stop me with questions. I think I was planning to say something about, let me see how I'm doing on time. Okay, so I think I can mention this briefly. I have time until 4, and then we have half hour for discussion. Is that fair, or should I stop?
Yes, that's right. No, that's good. That's good.
Good, thanks. Okay, so I think I have time to mention this briefly. So just to give some intuition, I want to say what differential privacy does and doesn't allow an attacker to do, or at least one thing that differential privacy says about the power of an attacker. Okay, so let's say, again, we have an attacker who's very determined to find out from the output of a differential private algorithm whether I sing in the shower or not. Let's say this is some information that's contained in the data set. And I'm not really limiting what the attacker already knows about me. Let's just say they don't know if I sing in the shower, but otherwise they can know all kinds of other stuff about me, and they now observe the output of a differential private algorithm, and they try to find out, do I sing in the shower or not? And I want to say that they cannot, right? This is personal information about me. I want to say that they cannot, that the attacker cannot figure that out. And here's one thing you can say that's implied by differential privacy. So you can kind of quantify the power of an attacker in terms of 2 numbers. One is the true positive rate, let's say, which is the probability that an attacker, if the data set contains the information that Sasha sings in the shower, then in this case, the attacker, in this case, we want to know what is the probability that the attacker correctly finds out that I do sing in the shower. So this is the true positive rate, the probability that the attacker correctly identifies that I sing in the shower. And the false positive rate is the opposite in a way. So let's say the data set says that I do not sing in the shower, but incorrectly the attacker says that I do. The probability of that happening is the false positive rate, okay? And normally a strong attacker would have a high true positive rate. So the attacker would have the ability to correctly identify that shower singers are shower singers, and low false positive rate. So the attacker would be able to correctly identify that people who do not sing in the shower really do not sing in the shower. But it turns out that with differential privacy, we have that the true positive rate and the false positive rate of any attacker who only sees this differentially private output, the output of a differential private algorithm. Differential privacy implies that the true positive and false positive rate will have to necessarily be almost the same. So basically, if the attacker has 95% probability to correctly identify that I sing in the shower when I do, they will also have a 95% probability, or say 90% probability, a little lower maybe, to incorrectly say that that I sing in the shower even when I don't. So basically, an attacker who has high true positive rate will basically almost always just say that everyone is a shower singer. In that sense, it's like a useless attacker. Okay, this is the kind of thing that differential privacy guarantees. Okay, so now the last sort of few minutes, let me talk a bit about how you achieve differential privacy. Somewhat basic methods, and I'll finish with some slightly more advanced methods. Okay, so Nikolov, you a couple of weeks ago talked about ways to achieve differential privacy for kind of more complicated things like training a neural network model. I talk about something very simple, which is answering counting queries, which is, again, these are just questions about the data set that just ask how many people in the data set satisfy some proper TP. Okay, it's a very basic thing you want to do with data. It's not obviously everything we want to do with data, but it's one simple thing we can try to understand really, really well. And I'll just focus on this since this is mostly an introduction. Okay, so let's say we want to answer a counting question like this. For example, how many men in this data set? The data set says sing in the shower. And a simple way to do this with differential privacy is just to compute the true answer and add some random noise. Okay, so for some reason we call differential private algorithms mechanisms. I'm not sure why actually. And a simple differential private way to answer a counting question like this is to compute the true count of how many data points in the data set correspond to men singing in the shower. And then you don't output that answer. Instead, you output that answer, let's say 30, plus some random noise. And there are many choices for the random noise. I'll give like one, I think that's intuitive to me at least. One thing you can do is you can flip S random coins, okay? And calculate how many times you get heads, and subtract from that how many heads you should get on average, which is S over 2, right? So on average, every other coin should give you heads. Okay, and now you take this random number, so number of heads in S coin flips minus S over 2, and that's your noise, you add that noise to the true count. Okay, and you can take S to be something that depends on the privacy parameter. Epsilon here is the privacy parameter in the definition. I won't talk about that in detail, but let's say S is some large constant, okay? Like large, but much less large than the number of points in the data set, for example. Okay, so, and what this does achieve differential privacy, you can prove that. It does take some proving, but you can show that. And what this achieves is that any single person's contribution to the thing that you're outputting, to the number that you're outputting, is obscured by the noise. Basically, if you have an attacker who maybe even knows everything in the data except the row that corresponds to you, even such an attacker, when they see this output, what they'll see is the one bit that tells the attacker whether, the one bit that says whether you sing in the shower or not, plus the random noise. But the attacker will not really be able to distinguish what's random noise and what's the information about this one person that they're trying to find something out about. Okay, so the noise successfully obscures the data of a single person. This does satisfy differential privacy. However, the noise is usually, if you have enough data points, usually this noise is much less than like the signal in the data. Usually it will be much less than the size of the data set. And in those cases, you can still detect statistical trends in the data while obscuring the contribution of a single person. Usually, however, we don't just ask a single counting question about a data set. So here I'll go back to like a census type example. So this is this table I took from the US Census website. Forgetting exactly which data product of the census that is. I don't think it's the 2010 census. I think this is maybe on the map. Doesn't matter one of the data products published by the US Census. And you can see every row in this data set is the answer to some counting query. The number of people in New York City, the number of people who are 18 years and older, how many of them are male, how many are female, and so on. There is a ratio of the two sexes, which is just the ratio of these two numbers. This is the only thing that's not a counting question here. Okay, so in many cases, you want to publish something like this, a whole table full of counts. Okay, this is how we summarize a lot of what's published in a census. This is how we often summarize, surveys, polling numbers. There are a lot of things that are just a combination of answers to many counting questions. And the problem here is that when you answer many counting questions, and this is kind of illustrated by these reconstruction attacks, every new counting question reveals a little bit more information about a person. So you can't really afford to add the same level of noise when you have many queries, because the queries intuitively can be combined to learn information about a person. It's like, again, think of each new query revealing a little bit more about a person. So the way we deal with this is we just add more noise. This is at least the basic way to deal with this. So one thing that does work is if you have K of these questions, you basically do the same as before. You compute the true count for every question, but now you add more noise to each question. So instead of flipping some constant number of coins, you flip a number of coins to generate the noise, where the number of coins grows with the number of questions that are being asked. So the variance of the noise you're adding has to grow with the number of questions. So these are kind of, let's say, two basic tools to achieve differential privacy. Now, for my last few minutes, let me talk a little bit about how you can kind of build on these tools and do a little bit better. And then I'll open the floor for discussion. Okay, so this is kind of the basic scenario. You have K questions, you kind of need to add, you need to, let's say, flip K coins per question to generate the noise for this question. So you can imagine we have a lot of questions, you need to generate a lot of noise per question, which is kind of problematic. Turns out that sometimes you can use the structure in the questions that you're asking to do a lot better. So here is a basic example, which I think is very illustrative. Let's say you're asking what we usually call threshold queries. So these are questions of the following type. Like, let's say the questions are, how many people have annual salary less than some threshold T? Okay, and we want to know the answer to this for every threshold in some big range. And basically, whenever you have numerical data, often this is the way you summarize the data, right? So this is a pretty reasonable way to summarize distribution of salaries, for example, I think. These are, if the range here of the salaries is of size R, to answer these R queries, it's like one query for each possible value of the salary. You need about R coins of noise per query. It's 3 even larger because of the privacy parameter, but let's say it's about R coins of noise per query, which is a lot of noise. It will really make the data useless in most situations, I think. But it turns out that you can sort of do much better by changing the queries. And you can really answer these queries with like a order of magnitude less noise, let's say. It's the, you basically can use exponentially less noise than this basic method. We say a little bit how this is done. And this is, I think, going to be the last thing I'll say that's technical. So Good. Okay, so how can we do this? How can we go beyond this simple mechanism of just like scaling the noise per query that we are adding? One basic insight is really, you don't really need to scale the noise that you're adding with the number of queries. Really, you only need to scale it with the number of queries that any given person can contribute to, okay? So this is often the same, but in some cases you can design the queries so that one person can only affect some small subset of the queries that are being asked. And the way you use this is you, instead of answering the original queries that you're interested in, you come up with a set of strategy queries where you design the strategy queries so that they have this property that any person it contributes to the answers of only a small number of queries. Basically, for any person, there are only a few queries that have anything to do with that person, that reveal any information about that person. And you can design some strategy queries that are not the original, that they're not these like threshold queries, what are the number of people of salary at most T. There's some other queries, but they have this nice property that only a few of them reveal information about any given person. And then you can find a way to reconstruct the answers to the queries that you actually do care about from private answers to the strategy queries. So you apply kind of a basic differential private mechanism to the strategy queries, which are not the ones you care about, but you find a way to reconstruct answers to the queries that you do care about from these strategy queries. And a nice insight of Lee McLaughlin, there's a picture here how you do that for threshold queries. I'll avoid that for now. I mean, I won't talk about this. But a nice insight of Lee McLaughlin, McGregor, and Rastogi was that, in fact, okay, so now you can ask how to even come up with such strategy queries. Maybe this is some hard design question, but it turns out that you can really use algorithms to optimize over all choices of strategy queries and all ways to reconstruct from them. You can solve this as an optimization problem and really find the best way to carry out this strategy. And in some of my work, now an old paper with Tawar and Zhang and a much more recent paper with Edmonds and Ullman, we've been able to basically show that in many cases, this way of answering queries where you come up with the best strategy queries to ask and then the best way to reconstruct from them, this often gives you the best possible differential private algorithms for these types of questions. I also mentioned that a variant of the strategy with sort of a lot more added to it because of the particulars of how the census works, but a variant of the strategy is also used for the 2020 US Census. Okay, I'll stop here with the technical stuff. There's one thing that I'll skip, and let me jump to some possible discussion questions, but we can discuss anything, but just mention a few. I haven't dwelt too much on the quantitative aspects. Well, I guess I did talk about quantitative aspects of these definitions, but one thing I didn't point out very strongly is that this differential privacy definition is quantitative. It comes with a privacy parameter that controls how much an algorithm can disclose about a person. And it's very unclear to this day how to choose that privacy parameter. You can imagine coming up with some sort of best practices, but we don't have them at this point, I would say. It's not clear how to converge on these best practices, at least to me. I'm sure many of you have much better ideas than I would. You can imagine some economic mechanisms to come up with a way, some like economic way to come up with like choices for things like a privacy parameter, and maybe for the many other choices that have to be made whenever you're actually implementing any of these things. But again, like aligning the incentives there in the right way seems quite tricky. I think it's an interesting problem. There is some recent work by Dwork, Coley, and Mulligan who proposed having an epsilon registry, they call it, sort of a differential privacy registry where companies and maybe even, I'm not sure if government agencies, but it is where companies using this technology can register what they do, what parameters they choose. This is one proposal, and I think there's a lot of space for work here. It's an interesting question, like how differential privacy, techniques like differential privacy align with regulation. Currently, a lot of the legislation seems to implicitly be still like in this world of person identifiable information. And it's not clear to what a sort of how you reconcile that with differential privacy type techniques. There's some interesting questions around, I think, very interesting questions around tensions between privacy and fairness that I would like to think more about. So privacy says that, at least differential privacy, but I think most sensible notions of privacy say that you shouldn't disclose too much about a particular person. And usually that also ends up implying that you don't disclose also too much about small groups of people, which means that differential private algorithms in particular give statistical information that's not very accurate when it's about small groups of people, like small subpopulations. So basically you get less accurate statistics for small subpopulations, which kind of makes sense in terms of privacy, because privacy says that you should get very inaccurate statistics about populations of size 1. It kind of makes sense that from there, the small subpopulations also end up, like you also end up having less accurate statistics about small subpopulations. But this seems to be in tension with sort of fairness concerns. What if this small subpopulation is some underrepresented minority group that you really want to have aggregate accurate information about? There's like an interesting tension there that I'm not even quite sure how to think about. And I'll stop here, open the floor, look at the chat.
Sasha, maybe you could stop the share so we can see everybody.
Yes, definitely.
Thank you.
And drink of water. Oh, it's also easier
absolutely.
to see the chat.
Okay, so I have a few people lined up here. Let me go to them, and then I'm seeing some hands up. Laura, let's start with you.
Great, wonderful presentation. It was really informative. So I have a technical question and then a kind of higher level question. So technically, and then you can be brief on this, I'm wondering how advanced these techniques are for working with data that are weighted. So my interest is in always inferring back to the real population, and sometimes sampling weights are introduced in the data to represent the true population. And I can imagine some of the methods proposed are a bit tricky if you also have to, on top of that, incorporate weights. And just wondering your thoughts on that, how developed that is or underdeveloped.
I think it's underdeveloped. I remember some conversations with applied statisticians who asked similar questions, and it seems tricky, and I think it's underdeveloped to some extent. Maybe also maybe I don't know what's the latest that's been done there, but it does seem tricky. I think it's worth, like, you're probably also thinking of things like stratified sampling, and it seems tricky. One thing that's interesting is that while sampling itself does not provide at least differential privacy, so just the fact that you're sampling from a large population doesn't necessarily provide differential privacy. It does help achieve much better privacy guarantees if you combine sampling with differential privacy. But when you do that in a stratified sampling way, when you then these things become much harder to understand.
Yeah.
And I think this is also related to this kind of problem of not being able to handle weights too well right now. Like,
yeah.
Weighted data points is what you mean, right? Yeah.
Exactly. Yeah. No, that was I think that's a great insight. And then my just big picture question, if I may, and it's just on what you said right at the end there. I was going to ask you about the idea that smaller groups, so again, because we want to relate this back to the real population and a lot of the work that I'm doing for identifying groups at risk, et cetera. So if we're less accurate in certain subgroups, is there a potential for bias and exacerbating inequities? Just thoughts on that.
Yeah, I think so. I think that's basically a better way to put the concern I had in mind. I have that concern, and I think that's also largely an open research problem that's been really maybe brought to the fore to some extent by the fact that the 2020 US Census will be done with differential privacy, and this was highlighted that one consequence of this is that you may end up having less accurate information about particular groups of the population, which can lead to inequities, because the census is used to, I guess, like allocate different kinds of resources. You really need to be careful there. So there's a little bit of work now, but it also kind of seems like a fundamental tension between two desiderata you have about like analyzing data. One is providing the most accurate information about kind of in like a fair way for every possible subpopulation, but at the same time, if you want privacy, it seems almost unavoidable that small groups are kind of hidden.
Yeah, it's a huge tension. Yeah, I totally agree. Thank you.
Thanks.
Thanks.
Leslie, come to you. You're on mute.
Sorry, I'm on mute. Yeah, thanks a lot for that this conversation, and particularly enjoyed the last comments about equity issues. I have a question. Are organizations that are adopting differential privacy, are they transparent about how these systems work? What does the public know about this? What might be the sort of literacy the general public would have about differential privacy, and what would be the best way of making the public aware of differential privacy?
That's another great question. One of the first implementations I knew about was by Apple in iPhones. And at least originally, they did not disclose how they choose the parameters. So eventually there was a patent that sort of would tell you how the system works overall. But the crucial, I guess, differential privacy kind of comes from this tradition of cryptographic techniques where the systems and the algorithms can be disclosed without hurting how private and secure they are. And differential privacy has this property, and I think companies can be relatively open, publishing research papers and finding patents and publishing kind of technical reports about how their algorithms work. But they're not always that open, I think, with the parameters. At least initially, there was a bit of tension. There were some stories in the news, at least about Apple. I don't want to say something that's not accurate, but I think it's fair to say Apple initially did not disclose what privacy parameter they're using. Eventually they did, but I think it is problematic when you use these techniques, but you do not say what parameters you're using or how exactly you're implementing them, because then they can turn into a bit of a fig leaf. That's my concern, that you use something that when you choose like a strong privacy parameter, when these techniques can provide very strong protection. But if you choose the privacy parameter to be very large, then they provide essentially zero protection. And then if you don't disclose how you're using, like how exactly you've implemented these techniques, you can end up just claiming, well, I'm using like the best protection there is, whereas really there's not so much protection. And then you just end up kind of avoiding scrutiny by claiming you're using this advanced thing, but you're really using it in a way that it's not doing anything. I'm not saying, again, like any company has done that, but I think that's a real danger. And so that's a real concern. I think this is partly part of this Epsilon registry proposal, is to have a system where it's kind of the standard for firms to register what they've implemented, how they've implemented it, what privacy parameters they've chosen. I have to look at this paper more carefully. I'm not sure if they have a proposal for how to incentivize companies to actually participate in that. I think they go by analogy with other public registries like that, but I think people here who know more about public policy can actually say more than I can.
Thanks. Thank you.
All right, thank you very much. Matthew.
Hi, thank you very much for this talk, Alexander. It was excellent. I wanted to ask you, and I realize now actually this may be a similar question to Christina's in the chat, but my understanding of the epsilon, the privacy loss function, is you sort of tune it so that you can only do so many queries before you reach a certain level of privacy loss, and each query you're asking sort of increases that privacy loss. How does this work though with like a dynamic data set where the data might change over time, or like even if you just have one data at one point and then you say you add another 1,000 people to a health study, how will that affect the privacy loss? Does that reset the budget in any way, or is there anything that it affects there?
Yeah, that's also a great question. And sorry, every time I say it's a great question, kind of means I don't have a very good answer. But it's definitely something people are looking at. It's an interesting research question. It can also be a little bit tricky when you get new people arrive into the system, and then they become a part of the data set, and then you start releasing stuff about them as well. But that's usually maybe the smaller concern, because until now you haven't released anything about these people. Now they become your clients and you start releasing stuff about them. That's a little bit of a smaller concern because you don't have so much like compounding of information about the same people. What becomes really tricky is when you keep releasing new statistics about the same customers over and over again, which is actually also true in some of these industry implementations as well. They also really have to grapple with this kind of problem. For example, Microsoft is using differential privacy to collect statistics about, I think, like people using Windows, and it's usually the same people using Windows like over many, many years. And every new time they like collect and release some information about how Windows is being used or how their software is being used, they're disclosing a little bit more and like losing some epsilon about the same people. So there's like some additional privacy loss about the same people. So there's some ideas about how to limit the number of times you have to kind of update your models. So the thinking is around, like the technical tools at least, are around trying to detect when do you have enough new information that is warranted to really do an update. And you try to do this as infrequently as possible.
So it's sort of at a point where it almost becomes a new data set to a certain extent.
Yes, right. The thinking is that most people, most of the time, do kind of the same things over and over again, and you don't want to really cost them privacy if they're not doing anything different. Right. So at least that minimizes some of the privacy loss, but it seems like a hard problem. There may be no perfect technical solution. Maybe this is one problem where we really have to talk about like data minimization and how do we minimize, like what is, maybe there should be some also like cost benefit analysis here. So there's some technical work. There's probably some non-technical like conversations that also need to be had. Like, I mean, not non-technical, but like outside of just publishing algorithms and doing computer science.
Okay, well, thank you.
Christina, did you want to jump in on this conversation too?
Yeah, no, it just, I think the economics and the public policy of this may be first order, because you said what would give firms the incentive to register. And I think if you have a set of observations that are going to be queried over time, and the privacy, the epsilon that you need to maintain their privacy therefore increases over time, you could actually see strategic interactions of firms wanting to get in on this game early and register with less noise, because everyone who comes later is going to have that plus something. And so actually the economics of the strategic dynamic interactions would feed directly into the computer science on what that epsilon should look like.
Oh yeah, that's interesting. Yeah, at least if you try to have some limit on how much privacy loss there should be, I guess firms that come later would need to add more noise to kind of not.
You could draw an analysis with like bidding for like bandwidth, right? And so if there's only so much bandwidth of privacy before it's no longer useful, firms that get in early and can claim some of that, you could actually see like a strategic interaction game there that economics actually has a lot of tools to address.
Okay, that sounds cool. I like that.
I just wanted to also offer another economist policy thinking thought on this, which is to say, so the presumption of a lot of these methods is, we're looking for a 100% technical solution to something that's probabilistic behavior out in the world, right? So, like we have to think about like who's going to be engaged in these attacks, what's the cost of the attack, what are the other methods like? So that's why I sort of wanted to go to that, thinking about just even the data sets, right? Because you can also put those, and this is like Lisa and David's work on, a trusted computing environment, so that so I think we may be looking for, the capacity to say, we've reduced the probability of this kind of attack by this kind of attacker. I'm just saying, sort of taking it a bit out of the mathematical framework, which says, okay, what we want is we want a mathematical proof that nobody, with infinite resources, motivated by who knows what, right? And to say, actually, we need to start adding some costs and benefits to those efforts as part of our thinking as well, I think.
Yeah, I don't disagree. Yeah, like yeah, that's an excellent point. There's a lot of ways you can mitigate the risk of disclosing private information, and I think it does matter what else is done to the data, who has access to it, how is this access controlled. All these things matter. Like, we had these conversations with Lisa and David and Nicola as well, that often this sort of personal data is not necessarily released to the public, which is, I guess, the most risky situation. Often it's used internally by maybe one company or several companies want to somehow collaborate. And then, yeah, the situation does seem different and the risks seem different. I do come a bit from this worst case mindset, but I agree that what other things you're doing to protect the data should come into the calculation.
Right. Great. Okay, thanks. And Nisarg has been waiting patiently. Nisarg, go ahead.
Yeah, no worries. Thanks for the great talk, Sasho. Really had fun kind of seeing the different initial approaches to trying to prevent the attacks and why they don't work. So there are two kinds of attacks that I can think of. One is a passive attack where I'm given the data sets and now I'm trying to identify some kind of personal information. And one is a more active attack, which is something that Ron also mentioned in the chat, where if I know that Presto is going to release a data set, I take a few trips actively kind of with you, and then I inject myself into the dataset, and then by afterwards, once the dataset is released, by looking at this dataset, I can maybe find out more. So have people looked at the kind of the difference between the power of passive versus active attacks with differential privacy or some other privacy definitions?
I have seen almost none of that. The one thing that rings a bell here is maybe a little bit different from what you're saying is, in crypto and security, there's like a lot of work that looks at all kinds of side channel attacks, because usually like, crypto works really well, but like like the algorithms are great, like they're like very, very hard to break. What is much easier to break is if you can use a side channel attack. So things like timing attacks, timing how long the computer takes to like churn some piece of information and trying to use that to kind of make a guess of what is the computer really doing. I think there's a little bit of work on like, can you do side channel attacks against differential privacy? Maybe this is one kind of active attack that I've seen people think about. But that's the only thing that comes to mind. Yeah, it's an interesting question. This is more in the realm of, can you still break differential private algorithms using side channels? Even though the algorithms have these guarantees, there's still like sources of information that maybe you have not accounted for.
Right. So I was thinking like this can also become kind of a two-player game, right? Where an attacker is trying to find the best data to inject into the data set so as to break privacy. And the kind of the principle is trying to maintain privacy, and then maybe there is some kind of game theory that also comes into play here.
Yeah, sounds interesting.
Something for us to chat about later.
Yeah, maybe we can chat about some game theory. Yeah, sounds interesting. The one thing that makes it difficult is makes it difficult to limit the kinds of attackers that you're going to. What do you want to say? I guess differential privacy aims at like a silver bullet solution that works in all kinds of situations and doesn't force you to limit what kind of attackers you may have. But I guess back to Gideon's point, in many cases where, like in many cases, it may be reasonable to make some assumptions about actually what the attackers can and cannot do because of other things you've done to protect your data. It's
right.
Yeah, I think it'd be interesting to, I don't know whether or not we've got any empirical information about that, right? So like what are the, like, so because at the end of the day, there's cost to this, right? You sort of emphasize there are costs in the accuracy of the models, there's cost in the computation. So in order to decide, if we're going to make those decisions, we're going to have to know something about, okay, so what's the likelihood and expected cost of an attack? And I don't know if you've heard of any, but I myself have not heard. It's not my area specifically on anybody trying to put anything onto the probability of these kinds of attacks, the size of the attacks, and so on. Lisa, I saw you pop up on the screen. Do you have anything on that? No. Okay.
Not on that specifically.
Okay.
I think there's a little bit, and maybe even Nicola mentioned this 2 weeks ago. There's now a little bit of work that tries to see how feasible some attacks are. And in some cases, right, because I guess what I can say is if something does not satisfy differential privacy, there's a theoretical attack, but that attack may be completely infeasible in a real world scenario. There's been some work to try to see, well, let's take something that's not quite differentially private. Maybe the privacy parameter is pretty large. Can we actually have a real world feasible attack? And there's some work over maybe just the last year trying to come up with realistic attacks that kind of match the theoretical guarantees of differential privacy in some sense. Yeah. But I haven't seen this kind of detailed like cost and benefit analysis. I've seen more like computer security type work where people try to come up with realistic attacks, but the economics of cost benefit analysis and quantifying risks that I haven't seen. Right.
Okay, and we'll go to Lisa for the last word here. Comment.
I get the last word. That's awesome.
You can close the conversation.
We've had lots of conversations about that kind of relationship between legal definitions and these sort of technical ones. And so I'm always struck from my perspective in law when I hear this kind of research presented, because when early on you're saying, talking about sensitive information, you talked about private information, talked about personal information, those all have different legal meanings, actually, just like they can't even be grouped together, which doesn't matter for anything you said about any of it. But it's just kind of when you move into these broader questions that Julian's trying to push us into, it gets really complicated to kind of figure that out. But I had a question about in the differential privacy literature. I'd be really curious if there's any reflection on what makes this idea of kind of singling out information, being able to say something about a unique individual, that's the privacy issue. Because I mean, generally data protection law was worried about personal information because they're worried about identifiability. And so you can like learn something about a unique individual in a data set, and that person is still not identifiable for the purposes of the kind of legal definition. So they come apart. And the identifiability, which isn't necessarily a good thing, that law ignores this question about kind of learning something about a unique individual. But the one of the reasons why identifiability has had such a kind of hold is because, when you're identifiable, that's usually means a kind of, you're identifiable in some socially relevant sort of way. Like, if people know your name or your address, or they know you're like the person down the street or who works in that store, or maybe you're being singled out by, an organization who's going to deliver you targeted ads. So they don't know your name or address, but they know that the person they're, doing business with has the following sorts of attributes. So there's some kind of socially relevant connection that identifiability is trying to track. And the idea of just learning something unique about an individual doesn't capture that. And it seems relevant in the law, at least for some sorts of things. And trying to sort that out is really tricky. And I'm just kind of curious as to whether there's like reflection within the differential privacy community about those questions, or they're just sort of taking, starting from this point of, we're going to think about this in terms of learning something about a sort of unique individual.
Yeah. So there's one paper I can think of that tries to do this, say something mathematically about maybe one or two, and and the point they're mostly making is that just knowing something's differential privacy doesn't, just that piece of information doesn't necessarily tell you whether people are identifiable or not from what's being output by the differentially private algorithm. But I think there's very little there, and I think the kind of computer science community that's working on differential privacy, I think we don't know how to formulate being identifiable in a satisfying way. I think we struggle with the fact that being identifiable, like part of being identifiable, also, so part of that is who is doing the identification and what they already know. And that seems important, and I think we don't know how to capture that, like mathematically in a way that we can say something about. That's also what I did. We were in Berkeley, maybe.
Sasha, I'm going to interrupt you just for a moment there, because I do want to make sure we let people go, but we can stay on and continue once we release everybody. But I want to say thank you for a wonderful, wonderful talk and lots of conversations to have. Just for next week, we have Shreya Sakar from Rotman Management talking about learning product rankings in online retail, diversity, robustness, and manipulation. And I'll look forward to seeing everybody there next week. And thanks again, Sasha. I'm sorry to interrupt you, but we'll let everybody go if they need to head to that next Zoom call.
I think that was basically what I can say now. I probably also need to think more about this. I just remember having a conversation with Kobe Nissim about this, as someone who I look up to as like a person who thinks about these things.
I think you might be the only person who's doing interesting kind of
at the intersection of like law and privacy.
Yeah.
Yeah, it's very interesting work. And I asked him, I said, hey, I think what I'm reading in or what I'm hearing from people is that laws really talk about being identifiable. And he basically asked me, okay, how do you define that? Have you thought about defining that? And yeah, I'm not sure how to define that. In the same way that we figure out how to define privacy and differential privacy, I think we don't have a satisfying way. And maybe just because it's a bit messy and it has to be. I'm not sure.
Yeah, I mean, lots of law is like that. It's even worse than you think, because if you look at the statutes that use personal information as the kind of way in which we figure out what we regulate, there's all sorts of policy considerations that are actually also playing a role in the interpretation of the term personal information. Sometimes very self-consciously and sometimes completely implicitly, but there's just no way to understand what's going on without all sorts of considerations that have nothing to do with this more technical question of identifiability. Right. And then even that technical question of identifiability is very, very difficult to kind of parse, except in these sort of general ways. So it's way messier than it looks when you say, oh, we're going to regulate personal information. So
right.
which is difficult then to make technical standards around it. It's difficult to then harmonize different regimes that regulate personal information. It's difficult to do all the things that we think are important if you're going to create kind of a regulated data ecosystem that protects privacy. So it's like a super important area, but yeah.
I think it's worth having more people from different areas think about these things, not just Kobe, I guess. I agree. The technical definitions don't and probably will not capture kind of the social cost aspect of like a privacy leak, or of doing something. Like it is, depending on the person and the situation, the social costs can be different. And I'm only starting to think about these things more seriously. I think it's very important. I agree.
I think this is our sweet spot for our interdisciplinary crowd here. So happy to have you part of the conversation. I'm going to have to jump to something else, but thanks again, Sasha. It was really terrific.
Thank you. Thanks, everyone.
Glad to have you on board. Thanks. Bye, everybody.
Same. Bye.